Now I will start to talk about the proof of limit case uniqueness. Using the method of moving spheres. And the moving sphere method is a powerful variant of the moving plane method. You can think of it like the conformal symmetry of equation will lead to conformal symmetry of solutions. And here for me, the equation is the Euler-Lagrange equation. And the middle step, I'll call it obtain symmetry of solution. So in particular, in order to obtain symmetry of solution, what we do is we do inversion with respect to sphere. Maybe that's where it got its name. And also for me, both the moving plane method and the moving sphere methods rely on maximum principle of the equation. So you can think of it like it's the maximum principle manifests itself in all kinds of different forms, and you try to make use of that so they can prove uniqueness of solutions to the equations. And the moving sphere method started by the work of Yan Li and Meijun Zhu in the year 1995. They originally were trying to solve an equation related to the Yamabe problem with boundary. And then later, people also realized that you can also use the moving sphere methods to solve integral equations. I want to talk a little bit more about the notation concerning inversion with respect to sphere. And the picture is like, think in terms of the upper half space. This is Rn minus 1. And then just think of V0 as a point on the boundary. Consider a sphere of radius lambda. So this is lambda. And we're considering the inversion with respect to this sphere. And we denote it as phi of lambda V0. By direct calculation, we could get that the conformal factor is going to be like this. And we will denote the interior of the half ball as b lambda V0 plus, where the closure is taken in the entire Euclidean space. And when we're running the moving sphere argument, we will consider, to begin with, we consider a function that is C1 on the unit sphere, and that would be the solution, that would be a solution to the Euler-Lagrange equation. And then we define a function that is in the upper half space, which is f composite with the function psi, where psi is the conformal transformation between the upper half space and the unit ball that we defined before, and adding natural log of the conformal factor of the of C. And what we call the inversion with respect to sphere is we consider what happened to the function f when we take inversion with respect to sphere. When we do inversion with respect to sphere, we obtain a new function f lambda V0, which is going to be the function f composite with the inversion with respect to sphere, plus natural log of the conformal factor. And similarly, we will also need to consider what happens to the hyperbolic harmonic extension of f. So if we consider the inversion with respect to sphere firstly, and then we do the hyperbolic harmonic extension to the upper half space, then this is what we are going to get. In order to run the moving sphere argument, we need to go through 3 steps. The first step is called start the sphere, which is we're going to compare the function f and the function f lambda v naught. We're going to say that one of them is going to be less than the other one inside of the sphere that we do inversion. In terms of picture, it is like we're considering the upper half space. This is Rn minus 1. And then if we consider the center is V naught, and that, let's say this part is lambda naught. And if we consider the big sphere here, then if you choose a sphere that has radius less than lambda naught, let's say here this radius is lambda, then if we do inversion with respect to the green sphere, we're going to have the original function will be less than the inverted function. The comparison actually happens on the boundary, so it is this. The second step is to prove that the critical lambda naught bar cannot be infinity. And the definition of lambda naught bar is to take supremum of this set over here. And this set will not be empty set just because of previous step. Step 1 makes sure that. And then we can take supremum. Step 2 is to prove that the supremum cannot be infinity. The proof is actually very straightforward. Just by contradiction, if lambda naught bar equals infinity, then we can choose a sequence lambda I goes to infinity, such that I changed the notation here. It's supposed to be on the boundary, and we will have this pointwise inequality, and then when you integrate, this is what we're going to get. Next step is the case, because the way we do inversion with respect to sphere, we add a natural log term of the conformal factor, and the conformal factor to the m-1 power will give you the Jacobian to do integration by part. And also note that these two terms add up will be just this part, so we arrive at the inequality over here just because of dominated convergence theorem. And this is the last step of the argument, where the statement is also very straightforward. It is saying that for any V naught in Rn minus 1 at the critical lambda naught, which is lambda naught bar, we are going to have the inverted function equals the original function. And the proof is more complicated. I can only talk about a sketch of it. The proof is by contradiction. If you imagine that there is a point V such that the original function is less than the inverted function, let me draw a picture here. So imagine this is Rm minus 1, and this is R. The point V naught is going to be here, and we draw a critical sphere. The diameter here is going to be lambda naught bar. And if we suppose there is a point V such that the distance from V to V naught is less than the radius, and also V is on the boundary, then if there is such a point V, then actually all the point W, which is over here, all the point here are going to satisfy this inequality. And this is by maximum principle of both the differential equation and maximum principle of integral equation, which is the Euler-Lagrange equation. And a lot of technical detail about the information of the function in tilde goes into making the maximum principle here works. And now we can choose a sequence lambda I that goes to lambda naught bar, such that each of them is actually assumed to be greater than lambda naught bar, then in terms of picture, let me just draw one of them. So this is a half ball, b lambda I v naught plus, and can also draw a bar here. And then by the compactness, these two functions are going to be continuous. Then by compactness of just the half ball, the closed half ball, there would be a point wi such that it would be the infimum point of the difference between these two functions. And this point, the value of the difference at this point has to be strictly less than 0. And notice that it cannot equal to 0 at this point. And this is also because of the maximum principle of the Euler-Lagrange equation. Now a natural question would be, where is Wi? And the answer is that Wi has to be in Rn-1, and also its distance to the center of the sphere has to be strictly less than the radius of the sphere. In terms of drawing, it's like this. This is b naught, and this is lambda I. Then Wi has to be somewhere here. The reason is the difference of these two functions, you can think of it as the hyperbolic harmonic extension of the difference. Then its infimum can only happen either in this part or in this part. But it cannot happen here just because we're doing inversion with respect to this sphere. So the two functions actually equal to each other here. And as a result, we know that W has to be in Rn-1, and also its distance to the center of the sphere has to be strictly less than the radius of the sphere. And just because of this, because this function is the extension of these two functions, and then on the boundary we actually get that this is just the difference of f lambda I v naught minus f, and this function has to be strictly less than 0. And also if we just look at in Rn-1, then Wi is actually an interior minimum point, so that if you look at the gradient, lambda bar is the gradient in Rn-1. So the gradient of this function actually has to be 0. And also these two functions depends on lambda continuously, so that we can take limit just as I goes to infinity. If needed, we can look at a subsequence so that Wi will converge to some point W0, and then firstly the inverted function will be less than or equal to the original function at the point W0, and this actually means that the distance between W0 and the center of the sphere has to be exactly lambda naught bar. This is because when the distance of W to the center is strictly less than lambda naught bar, then we will have f of W will be strictly less than the inverted function at the point W. And this is to justify that the distance between W naught and V naught has to be exactly lambda naught bar. And also we get the gradient at the point W naught has to be 0. And then we can use the Euler-Lagrange equation to calculate the gradient of this function when the distance of the point to the center is exactly the radius. And by calculation, we know that this is not 0, which is the contradiction. And that finishes step 3, and also finishes the moving sphere argument. In order to finish the proof of this theorem, which is uniqueness of limit case inequality, we need the help of the calculus lemma, which was used by Yan Li and Meijun Zhu. And this is saying that for any function that is C1 in Rn-1, you consider any point B in Rn-1. This is equivalent to our point V naught. There exists a lambda B, which is equivalent to our critical value lambda naught bar, such that f equals this transformed version of f. This is equivalent to saying that our version of f equals f lambda naught bar v naught. But the relation between their f and our f is like their exponential of their f equals our f. So just sort of like this. And it is exactly like this, but this formula is weird. And then you know exactly what the formula of f has to be. It's either positive or negative. And this finishes the proof of uniqueness. And also this finishes my talk. Thank you very much for your attention.